Yes, good morning, good evening, whatever time zone you live in. Today I want to show you some instruction codes. I plan to assemble with FASMG, just because it feels a bit more flexible. Let's include some instruction set and make a listing of instructions. And we are going to begin with a very simple instruction, 16-bit from the old days. Let's say this one. Alright, so we see in hexadecimal the code corresponding to this instruction. And now I plan to dissect this code. We could simply look at the table in the Intel manual. So the first digit is 2, the second digit is 3, so this is AND with general purpose register as first argument and extended operand, memory operand as second. But although this table is very useful and nice, I want to show you that this table in fact hides something. An important fact about the original x86 architecture. You see, the original x86 is in fact, I would say, kind of octal architecture. There are many things there that come in 8s. For example, 8 general purpose registers. And these registers correspond to octal digits, like this. 0 is AX, 1 is CX, 2 DX, 3 DX, and then SP, BP, SI, and DI. An octal digit is encoded on 3 bits. So anywhere where in the instruction code there is going to be encoded a selection of register, we are going to have 3 bits that encode such number from 0 to 7. So it is in fact a good choice to, instead of hexadecimal like here, write down the same numbers as octal. Let's start with 23 hexadecimal. On bits this is going to be like this. And for octal we need to split it into triplets instead of quadruplets of bits. So this is in fact 0, then octal 4, octal 3. Let me do a sanity check. Octal 4, 3. And now if you look at this table, you can see that these basic instructions also begin every 8 codes. So if an instruction is 00 something in octal, this is then added like here. Next is OR. This is 01 x octal. Okay, our instruction code was 4.3 in octal. This 4 corresponds to AND, as it should, because this is the instruction we assembled. And the next octal digit, 3 in our case, corresponds to the choice of one of these variants. As you can see, every single one of these basic instructions has in fact 6 variants. The last 2 are reused for some different instructions. So 3 corresponds to this variant, where the first operand is a general purpose register and the second operand can be register or memory. So now we know what the first byte means. Now the same for the second byte. Change it to octal. This is 0, 1 and 7. Is that right? What is the second byte? Well, let's take a look at manual. After the opcode, there comes a ModRM byte, and as you can see, it has fields corresponding to octal digits. 3 bits for this one, 3 bits for this one, and 2 bits for mod. Mod 00 is just a memory. Oh, you would like to ask about this nomenclature. Well, this is not a standard nomenclature. They use it for this table, but I don't think it's very important to understand why they chose these names. GB means a general purpose register byte size, and GV is general purpose register variable size, because it depends on the mode of processor of instruction. In this case, V is always 16 bits for now, as long as we are just original x86. Okay, let's go back to instruction format. So in this case, we have 2 zeros, or just 1 zero as an octal digit. This means that this is a memory operand. Then 7 is RM, so 7 corresponds to that memory operand, and 1 is our register code, so 1 is CX in this case, just as it should be. So we only need to explain the 7. Alright, this is our table. 16-bit addressing. Mode 0, RM7. As you can see, this is exactly the address that we expect here. And now you can see that 0 is just a regular memory operand, 1 is a general purpose register, and 0 1 and 1 0 for modes are just memory with displacement. And this is in fact everything that you need to decode any 16-bit instruction of the original x86. Well, if this was an 8-bit variant, then these codes do not correspond to 8-bit variants of all these registers, because only 4 first registers have 8-bit variants. And the other 4 are the high portions of the same registers. In the same order. So let's Let's try assemble this. Oh, perhaps with a small modification. Let's take a look at this one. 22 or 042 Octal. The difference between 3 and 2 is that 3 was variable size, 16 bits in this case, and 2 is 8-bit size. So CL instead of CX. Next one is OC 114 Octal. So this one is mod, it means that this is memory with 8-bit displacement. Another one, this is code of register, CL in this case. And 4 is code in display. 100 SI plus displacement. So this is and CL SI plus displacement. And displacement is provided in additional byte 1. Therefore, I hope you can see now that Octal system really makes things easier. When you write down the same numbers as Octal, then every digit is just a piece of information about that instruction, and you can interpret every digit separately. Alright, we can now move on to 32-bit processor. Let's try a similar instruction dot 32-bit. Oh, okay. There is a question, what was the reason for that octal format? I think this is an interesting legacy. Well, I'm not old enough to know exactly what was the original, but I believe PDP-11 architecture was an earlier architecture that highly influenced this design. If we take a look here, oh, this is very important phrase. The octal notation was just as natural for that old PDP architecture. And as you may know, PDP-11 architecture was a very important architecture for Unix and the original C language. So I believe that Intel was inspired by this older standard. Oh, there is also this interesting bit of information. I had once tweeted about it, that portable executable, the format that Windows executables use today, has a hidden PDP-11 instruction inside of it. These are my old tweets. There is a lot of interesting history here. And as you can see, Octal systems once again is important. It was even more important for PDP than it is for Intel 8086. Even jumps used the Octal system. Alright, enough about PDP. Let's go back to 32-bit instruction. And now you can see that the same 2-3 opcode is here, but not in the first position, but only after a couple of prefixes. It was in fact 86 that first introduced 32 bits and more than one prefix for instruction. In this case, 6.7 promotes the memory operand to use 32-bit addressing, and 6.6 promotes the register operand to be 32-bit. So we could compare with a few different variants. If there is only 6.7, it modifies only memory operand. If there is only 6.6, it modifies only the register. And another important thing introduced by 386 is the scale index based addressing. You may remember this table for 16 bits. Now let's find one for 32 bits. There is something interesting hidden here at 100 or Octal 4. This is SIB addressing, scale index base. And when this addressing is used, there is another byte after ModRM, SIB. And again, it has octal fields. When is this used? Well, 32-bit architecture allows us to have memory operands that use multiple registers and in any combination, almost any, with additional scale modifier. So this is already quite a complex instruction code. Two prefixes, we know about them already. Well, if we switch to 32-bit mode of the processor, the prefixes are no longer needed. The prefixes change from the default, so when we are in 16-bit mode, the prefixes change to registers to 32-bit. And when we are in 32-bit mode, the prefixes change into 16-bit. So by switching the processor mode, we got rid of the prefixes. Now 2-3 we already know. What does that mean? For 3 octal, 4 corresponds to end. So let's focus on the next one. 0C is 1/4 octal. 213 octal. We should compare with this table. Mode is 0. This 4 corresponds to memory operand, and this 4 selects scale index base SIB mode. So this 4 tells us that there is another byte, and it is SIB. Now, when we write this in octal, the 3 octal digits correspond exactly to scale, index, and base. Scale works like this. 0 is times 1, 1 is times 2, 2 is times 4 and 3 is times 8. So in this case we have 4 times index register. Index register is 1. So 1 it should be CX and base 3 B. Is that right? Yes, this is the address. Do you have any questions? Well, this is where we end with Octal system, because when we move on, the things are no longer octal. We can move on to 64 bits. Now, what is interesting about 64-bit mode, long mode, is that it got rid of some of the instruction codes to reuse the same numbers for different purposes. So, for example, this range of numbers that corresponded to a special short variant of increase register in long mode are no longer used for this purpose. You have to use a long form of the same instruction instead. And this entire range for 0 to 4F is used for rex prefix. This is a special prefix that always immediately precedes the opcode. Let's first assemble some simple 32-bit instruction in long mode. As you can see, it only has one prefix. In long mode, it is not 64 bits that are default. Default size for operands is 32 bits. So if we have 32-bit operand, we do not need a prefix to modify it. But for the addressing, the 64-bit register are default. So if we wanted to have instruction without prefixes, we would need to use defaults like this: 32-bit operand dot 64-bit addressing. Now, if we have 66 prefix, it modifies the size of operand, but it modifies it to classic 16 bits, like this. So how do we promote the operand to 64-bit? Let's take a look. This is a rex prefix. The structure of rex prefix is given here. As you can see, no more octal. For a prefix, we are going to work it in hexadecimal now. From now on, hexadecimal is going to be more natural. The high 4 bits corresponds to this digit 4. So when the high hexadecimal digit is 4, this is a rex prefix. And 8 is 1000. And this corresponds to the W bit. And as you can see in the manual, W bit promotes the operand to 64 bits. What are the other 3 bits for? Oh well, 64-bit architecture extended the list of general purpose registers. We no longer have just 8 like the Octal x86 architecture had. We now have 16 general purpose registers, and we need a single additional bit to be able to select from the other 8. And as you can see here, R bit is that additional bit for rec register field instruction. B is either for memory field if we do not have SIP, and if we have SIP, it modifies the code of base register. Let us make an instruction that uses this. One of the new registers as base, and perhaps one of the classic ones as index with scale 20. Now we have 49 prefix. So base register is one of the new eight new registers, the extended registers. If index was also one of the new registers, we have forbidden, and for B is like this. And finally, if we also have a register operand, that is one of the extended registers. This is now for F, and all the bits are set. Okay, do you have any questions? Would you like to hear something about EVEX encodings? EVEX is where things become really complex, I would say, compared to this. Rex prefix is very simple. And VEX and EVEX, especially EVEX, are quite complex in comparison. So, VEX prefix comes in two variants, 2 byte and 3 byte, and this is a bit like a grown-up Rex. However, there are some subtleties hidden here. To make a space for this new prefix, they had to reuse an instruction codes that correspond to existing instructions. These instructions are in fact ones that only work with memory operands. So, to reuse the codes, we have to use them in such a way that mod in ModRM field, in ModRM byte, mod field needs to be 11 or a 3 as octal digit. Let's go back to a simple 32-bit mode. This is the instruction LDS. C5 is the same byte that is used for 2-byte VEX. So 2-byte VEX also starts with C5, as if it was LDS instruction. However, LDS is only allowed with memory operand. So it is not possible to have LDS with mod 1, 1 or 3. And this works in such a way that the high 2 bits here are always set if we are not in long mode. Why? Because R is a bit that selects one of additional 8 new registers, so it is not allowed in long mode anyway. But wait, this would not work if it was simply R bit, because we need it to be 1 when we are not in long mode. Therefore, this bit is stored in 1's complement inverted form. As you can see, it is the opposite of what it was in Rex. When it is 0, it selects one of the new registers, additional 8 registers, and when it is 1, it does nothing, it selects one of the classic registers. These 4 bits are another register specifier. This time not split. With Rex we had to split the number of register into a separate R bit, and there's 3 bits selecting classic 8 registers were in the ModRM. So the second highest bit of this byte is the highest bit of this register specifier, again inverted. So again in 32-bit mode, outside long mode, this is going to be always 1. On the other hand, in long mode, we are free to use these fields however we wish, because in long mode there is no longer LDS instruction at all. In long mode, C5 is a free opcode. So only in long mode, VEX prefix works to the full extent. And this additional register specifier that we see here allows us to have 3 operands instead of 2 as in classic Intel instructions. We need to include additional instruction sets. So here we have C5, 2-byte VEX. Then E9 is a second byte of VEX. 9. Is that correct? The highest 2 bits are set, so an old processor would see that this is LDS instruction, but with mod saying that it uses 2 register operands, so incorrect instruction. So there is no conflict there. And if we interpret this as VEX, then we have R here, D here, L, P, P. Now, L selects the size of vector register. In this case it's 0, so this is a 128-bit vector. If we change it to LR1, this is going, L bits is now going to be set. EV. And PP is a field that encodes other prefixes, so that we no longer need to provide these other prefixes when we use VEX. And what is the longer VEX for? Well, as you can see, it has this MMMMM field that allows us to shorten the instruction code. Oh, I did not talk about this these long codes earlier. I should perhaps get back to this topic. You see, when Intel had to add some new instructions but run out of codes in this table, it reused this one, 0F. You can see that looking at the symmetry of the opcodes, here's push CS, push DS, pop DS, it should be pop CS here. But pop CS is a completely useless instruction. So this code was not really used for this purpose, and they reused it to create longer opcodes. So the extended opcode, code of extended instruction, would start with 0F and then another byte from the second table. This table. And then, to not fill out this table completely, to not run out of places here, we have additional extensions where the opcode is 3 bytes long. First byte is 0f, and then second byte is 38 or 3a. 0f 38 and 0f 38. As you can see, this table is not much used. And then, when we started using VEX, VEX allowed to shorten this 3-byte instruction codes, 2-byte and 3-byte, by encoding them within VEX prefix. So then you no longer need to provide a complete 0f, 3a and another code, another byte code. You just provide a full VEX prefix and the code, and in VEX it is encoded that if this field is 11, it implies that this opcode that follows VEX should be interpreted as if it was preceded by 0f3a. So, as you can see, with VEX things got quite complex. And then came EVEX 512 with extended VEX prefix. I should perhaps leave it for another time. You see there we have 32 registers instead of 16. So we need to encode registers with 5 bits, not just 4. We got far away from the original Octal design. So what do you say? Should we leave EVEX for another time? I do in fact think that we should stop here for now. If you have any questions, please ask. We can end with a small Q&A. Have a good day, SSJ Coder. See you next time. There are many more interesting things hidden in this table. We can easily make another episode or two. Alright, thank you everyone. If there are no more questions, I'm going to finish for today. I may continue the same hour tomorrow, if you would come. Thank you. Bye.